So this is the third lecture for this course for interactive session. So as earlier, we will go through the video on this week and then we will solve the questions. So this week's topic is vulnerability and savings. So until last week, what we were doing was we were talking about the index properties.
मैम स्क्रीन दिखाई नहीं दे रहा है।
So the index
नहीं, अभी तो था बट अभी गायब अब हो गया। नहीं, फिर गायब हो गया। ब्लैंक आ रहा है ब्लैक कलर का। यस मैम।
So we were doing index properties. Which were like were the characteristics of a particular soil. As I said that one way we get a sample, then we will do some characteristic tests, which tell us about the soil. For example, when you go to a diagnostic lab, you give your sample of blood and then you get some fundamental tests like आपका blood group कितना है, आपका से count कितना है, जैसे for example blood group कितना है, it tells you about your blood group, something about वैसे ही index properties they tell you about property of the soil irrespective of its ये कैसे present है then permeability and seepage. These are deep engineering properties. For that we can change. We can change these properties based on what is our requirement. For example, we want to form a drainage layer of, let us say, in a road or let us say an embankment. I want a drainage layer there so that any water that is sitting in the embankment gets drained from there. We will be learning about this while we do this. Let us say we get a drainage layer there, or we form a drainage layer under the exposed, surface exposed, so that all the water that is sitting inside it can go to the sides and it is not moving about so that the road is not get. So the drainage level, what we want is that the water should flow very fast through this. So what we want to do is we will create this drainage layer out of very coarse aggregate, gravel mostly we will create because we know that the properties of that gravel are freely draining. And how much permeability is required? This is governed by our IRC codes or IS codes, like how much permeability do we need in the road, how much permeability we need for the embankments. So we have that value, and based on that, you decide the gradation of your soil and form this kind of a soil which has this property. So it's an engineering property which you can change based on how place was caused. It is not an intrinsic property of the soil which cannot be changed. Okay. So engineering properties can be more than we discuss more engineering properties later. But right now we can discuss about permeability and seepage. So permeability is like it is we can say it is analogous to, for example, we used to study that when current is going through a conductor, there is a resistance to this flow. That in the same manner, when water flows, if the water is flowing through a pipe, it will not see any resistance in this open area. But if I fill this pipe with gravel or sand or anything, when the water reaches here, up till there, there is no resistance. But there is resistance to flow when it is going through this soil. After this, again, there is no resistance. This resistance, how much this matrix of soil will resist this flow of water, depends on the permeability of the soil. If the matrix is very sparsely packed, for example, it has huge gaps, like in case of gravels, so the resistance will be lower. But if the matrix is clean, the gaps are very small, it will show very high resistance. So the gravel will have high permeability and the clay will have low permeability. And seepage is just the quantification of how much flow is taking place. It's basically the quantification of permeability, as in not permeability, but seepage is like now if you combine this up till now, if I just give you the soil, you can tell me the permeability of the soil because it is a property of the soil matrix. But without, if I tell you what is the seepage here, you won't be able to answer because seepage depends on how much flow you are allowing. What is the Q that is going inside? So that then the flow out. This will tell you the seepage that is taking place on the soil, and it will be different. It will have different inflows. So permeability is a property of the soil matrix itself, but the seepage will be a property of the matrix plus the flow, inflow. So component of iron table. Permeability and seepage is started in the deep flow itself, and we had only discussed the phase type. Okay, we can start from here. Permeability and seepage. Subsurface water, saturation zone, water table. Okay, let's take this diagram. Subsurface water is all the water found beneath the Earth's surface. It's like this groundwater. This is your ground surface, and this is your water table. Anything below this is your subsurface water. And above this subsurface water is a very green part. It is in my ground. This is my ground. This water table basically what this is the extension of this the level of the mean sea level actually. So when your land is above this, you will have water table below it. Because as you know, it is not flat. There are places where your ground will be above this water table, places will be below them. Below the water table, you will get a water bottle. When it is above the water table, you will get the water bottle. It can be like if I go hundreds of kilometers beyond this, can have a very low water table. So if they have a very low water table, it can have a high water table. That is why near water bodies will always find low water table. And let us now say that this is our soil and this is our water table. So based on the soil structure, let us say that this is C5 soil, clay plus a fine grained soil. Uh, this is a clean soil. Fine grained. The pores are very thin. The pores are very small. They are very small now. You can think about it like if you have a tissue paper and when you dip it in water, you can see that the water will start to rise even above the level of the water there. You will see that the tissue will get wet above this level. Why? Because why this upward movement of water takes place? This is because uh, the tissue is a porous material and the pores are very small, so small that the they are of you can say that they can be of comparable uh, the radius or diameter is comparable to the molecule size of the water molecule. It does not mean that it is lower than the water molecules or it's at a molecular level. What I mean is that usually we say that this is the water level, isn't it? But uh, we ignore the effects of the boundaries because the trough is very large, and even if there might be a meniscus there, it will be very small as compared to the whole length of the trough. But now, if I reduce the size of this trough so much so that now, right now, this could have been 0.005% only, और इससे भी छोटा. But now जब मैंने इतना छोटा इसका साइज रिड्यूस किया है, I can't now actually assume that the ends are not affecting the level of water. So if usually I took this as level of water, now I have to take this as level of water. This because these van der Waals forces that act on these uh, ends are now not uh, ignorable because this size of this capital on this group. So I hope I'm making sense. If you have any quick conclusion, then interrupt me. I know if you find my explanation a little bit or find it. Okay. So as I was saying that now these pores are so small that the van der Waals force has to be taken into account. So what happens in this is that the water gets atta- attracted by these walls such that it rises up. So this is the capillary. There is a minimum diameter for capillary action to take place, such that any diameter above that action will not result in this capillary force. So if you have, let us say, uh, something that does not have tiny pores, okay, you will not see this effect in that. You will just see that I am prepared here and that's it. Water is not rising above. So in the soil, the water table is here. Let us say that the fine grained soil here, the fine grained soil is clay layer here, which has very fine pores. So this capillary effect will come into action and water will start to rise up to a small height. Not too much, but small height. So up till here, let us say all the pores are filled with water. Now you see that this is also saturated. So this is also saturated. But this is above groundwater level and this is below groundwater level. And as you remember, I told you that anything below the groundwater level, we will take the unit weight as submerged unit. But here we will take saturated unit. And also, when we talk about effective stresses are the total stresses minus the pore water pressure. The pore water pressure here actually is negative in this capillary zone because as opposed to what is positive, we are taking positive the direction of the gravity. But right now, your water is moving opposed to this direction. Yeah. So suction basically. It's not we are not pushing the water, we are pulling it. So we get a negative water pressure here. This is a capillary zone. Just capillary zones just above the water, subsurface water. If it is clay or fine grain. If it is gravelly, you will not see this capillary fringe. Okay. So you have a subsurface water, groundwater table. The property for this is that you have a pressure of atmospheric pressure of 0 here on this surface, and then as you go down, your uh, pressure will increase. Just hydrostatic pressure we will see hydrostatic pressure decrease. Okay. So the first property is this. Second property, I said that the second property was that below this we will take gamma submerged. Then the capillary fringe, I told you, capillary fringe will be above groundwater table. It will be only if fine grained soil is present above groundwater table. It will have a negative pore water pressure. Okay. Then we talk about saturation zone. So saturation zone will be this uh, capillary fringe, groundwater table. This whole will be saturated. So because as I said that there will be a small height up to which the pores will be filled with water. Then uh, aeration is known occurs when the water table and the surface. Uh, uh, Just between the water table and the surface comes between two sections. There is a capillary trench. So this is groundwater. This is capillary water. Capillary water, what will happen is that there will be a section of capillary trench that is completely filled with water. But there will also be a section that is partially filled with water. Okay. Uh, Not for the water table. Then there is an intermediate well. This will have partially saturated. Again, on the percolates. So we tend to concentrate firstly, not propagated by plants. Then the soil well transition of soil well is constituted by evaporation, wetting and drying as per uh, weather conditions. And we are talking about surface tension capillarity. Okay, as I was just saying about capillarity. When you reduce the size of the fluid through which water has to flow, this is water. When you reduce the size so much that now this is comparable to the size of the comparable does not mean equal or smaller. Comparable means like 5 meter is comparable to 100 meter. If I say sorry, 100 meter, I will not say 95 meter is approximately. But I can say that 95.0001 meter is approximately equal to 100. So it is comparable, but we can no longer ignore these cells. So, basically, we talk about two kinds of adaptive chemistry, that is adhesion and cohesion. Cohesion is the attractive force between like particles. For example, the force of attraction that keeps the water molecules uh, connected, between the water molecules will be the force of cohesion. Or in case of soil, it will be the force of attraction between the soil particles. Adhesion is something between unlike particles. For example, if you have an interface like a wall, boundary, so the force of attraction between this interface material and your um, flow material. Here, the cohesion will be in the particles of the water. But adhesion will be, let us say, this is glass, between glass and water. So, some fluids, they have, it's not only about the fluid, it's about what is the combination of the two things that we have there. For example, if I would coat this glass with oil, then I would not see a layer forming like this. I would see a layer forming like this. Because soil will, water will repel this oil. It's not miscible with oil. But yeah, with certain interfaces, they can show cohesion greater than adhesion or cohesion less than adhesion. Here, what will happen with soil, with water, is that you will find greater adhesion as compared to cohesion. So the water molecules will start to stick to this interface and you will form a capillary because of this surface tension. Why it is called surface tension? Because uh, why what is the term? Any particle inside will have same force in all directions, same force in all directions, same push, same pull in all directions. But the surface particles will have the pull in the downward direction, but not in the upward direction. So they have to interface at the surface, the boundary line. So all these surfaces will have forces like this. What this results in is a net pull inwards, isn't it? So that is why, so it feels like the surface is stretching. It becomes like this. That's why it's called surface tension. And from this formulation, we take if this is the tension developed due to the surface tension, and then alpha is the angle at which this means this is found. This angle will tell us about uh, basically how much it is the line of action of this tensile force, and then this is your alpha. Then you equate the weight of water that has risen into this capillary flow for that you have already studied it, that we take a drop and we put water in it, then we put a standpipe. It has a very small diameter and see that the water goes inside and it rises to a level and we are interested in learning how much height this water rises. So this is the height of the capillary. This height of the capillary will depend upon how much tensile force or surface tension basically this material, this fluid shows. Then we equate the weight of this. We can say that the tensile force is responsible for the rising of the water level, and opposing this is actually the weight of the water in volume. And uh, this will be in equilibrium. When the tensile force was greater than the tendency to go down, rise and common equilibrium uh, at HC. That is how we calculate this HC. And as I said, below your water level, you will have a hydrostatic will be positive. But above it, you will have a hydrostatic pressure. It will be capillary pressure will be negative. That is why all this HC will be a negative flow. Okay. Now, this was about what if we have molecules, how these goes up to oxygen behind that. Now we will talk about when water flows through this basic law that we have for flow of water. So it's the Darcy's. So what Darcy did was did some experiments, and in these experiments, what we did was we took soil ball, then you see this is filled with soil. Okay, then we let some uh, amount, some discharge of water flow through the soil. Okay, and if you let's say the soil is almost fertile, I have a horizontal soil that is not very beginning, and I put the manometer here or stamp collector or stamp here, and I put some water inside. I will see that both these dam pipes rise to the same height. Okay, so both these will rise to the same height. Even if I didn't look that, okay, so what will happen is I will have the same bonding. But if I fill this with soil, and now I let this water flow through this, there will be a decrease in the hydraulic flow. I see a decrease of hydraulic head as the water passes through this soil. This is because of the permeability of this material. It is not 100% permeable. So what she showed was that this uh, hydraulic loss of hydraulic head, and it depended on the length of this sample. So let this be L. So the hydraulic gradient was loss in head over unit length of sample. This was integrated as I. And Darcy's law states that the velocity of flow through the soil is directly proportional to its hydraulic gradient. or velocity of fluid flowing through a soil matrix is equal to permeability times hydraulic. So these were the experiments he conducted, and this is the result. This is the result he got, that V equals A I, or velocity of flow equal to the permeability of the matrix multiplied by the hydraulic weight. V is the discharge velocity, I is the hydraulic weight. So soil structure and permeability. We can talk about what this is basically the permeability of the soil. So what do you think should be the properties or characteristics of soil which affect your permeability? So here I would like to say first, there are some kinds of permeability. Some kinds of permeability. Basically, there are two terms that we sometimes use interchangeably. What we should have. One is permeability, another is hydraulic conductivity. Permeability is the property of only what soil makes. And your hydraulic conductivity is the property of soil matrix as well as the fluid, such that your hydraulic conductivity will be kappa permeability multiplied by divided by therefore this formulation. So
They're coming straight.
the conductivity conductivity is equal to intrinsic permeability multiplied by rho G rho U, where rho and mu, rho is the density of flowing liquid and mu is the viscosity, dynamic viscosity. Okay, so this is your intrinsic permeability, which is only dependent on the soil matrix, and this is your hydraulic conductivity that tells you about the complete picture about how the particular fluid will move through the particular style. Because if in place of water you have oil, you know that it has a higher viscosity, you know that the permeability, isn't it? Or if it is very dense, then it will have a really different properties. So now if you talk about soil structure and permeability, first thing we can say is that we know if there are too many voids, permeability will be high. Not too many, because, as a matter of fact, the void ratio of fine-grained soils is greater than that of coarse-grained soils. Size of voids matters because if the size is very small, then you have that capillary action and you will get very high resistance to it. Granular soil, the blocky will have, see here also we have larger voids, but if you can see the path of flow is very long there. So as we saw, we will take I, but I will be times by L. As this length increases, the length of this path of flow increases, we have a different value. And then plate we will have a much longer flow path. Total handle is not different because is okay to the whole experiment. So one of the formulations, you can say empirical equation, driven for permeability was um, 10 times d times square and for x. So d10 is from your gradation. We can call this an empirical equation. It will not have any logic behind it. It will not have any physics behind it. But it is something that experiments may have some a good resemblance to time again. Then gravel will have a higher probability, 10 to per month. So sand will have lower in fine sands, courses, much lower. Then sills will have even lower than we have clays. Factors affecting formation of probability. Size and shape of the soil particles. Void ratio. Probability increases with increase in void ratio. It actually is not, we can't say that. Don't think we can say that. If you will increase void ratio, it will be there is this equation K is equivalent to UW, C over mu, something that we already discussed, times 1 by Ts S square T square. Just ignore this for now. This is basically about the flow path. The flow path is very tortuous. For example, we might say, we can say, this is a very tortuous flow path. This is this has low tortuosity. S is the specific surface area. And CS is the shape factor, what kind of shape particles. Uh, let us replace this by shape function or not. We can replace this by viscosity, mass viscosity function. But when we talk about void ratio into equilibrium plus two, we can't simply say that increasing void ratio will increase your permeability because the relation is not linear. Okay. Shape and size of soil particles, just like we just talked about the degree of saturation. And composition of soil particles. Sanding fruits. This is not important. However, for soil with clay minerals, it becomes the most important factor. Permeability. In this case, depends on the thickness of the matter where are the soil particles. So where we are talking about the diffuse double layer. Then we're talking about determination. We might have covered this in class. Falling head, punching head, and green position. Then we are talking about layered deposits and permeability to these layered deposits. Um, so you can have, for example, sedimentary deposit that may have different permeability because as you over the years as soil deposits, what happens is that the overburden over the layer increases, and as this overburden increases, this soil has higher and higher load on it. And this higher load will result in a tighter packing of the particles. So this will have a lower maybe void ratio. This will have maybe a higher void ratio. This will have a higher density. This will have a lower density. So based on this, we will have different strata, different permeabilities. Now, if the water is flowing in this way, water is flowing in this way, how do we calculate the effective permeability of this kind of a layered strata? Other thing is when we uh, make an embankment, what we do is first we take one layer and then we roll over it. Let us say that I was rolling with a fork and I was imparting the force S. Then I put another layer and I again impart F there. What this F has been imparted to the source. Then I take another layer. I impart F there. This will be plus F, this will be plus F. So you will see that this will be more dense, less because of the rolling effort I have put in sequentially. So considering flow to be parallel to the bedding plane, as I said, that if the flow is taking place parallel to the bedding plane. Okay, A is the total area, A is the hydraulic gradient. Then we have the total flow must be equal to sum of the flows of each layer. So this flow here, flow here, flow here, and we just start. But if it is perpendicular to the bedding plane, then we have a total flow which will be given by this. This will be our related and effective. Okay. If we cover both the lectures, now in that is we can start with the questions. Um, okay. It was about permeability. Uh, What's the case we will be talking about? First, what are the cases in which we are permeability of water? When you have, let us say, bound and water has been bounded there, and there is a sheet wall there. If you say uh, there is this area which has been filled with water, and I have placed a sheet wall here to block this water from flowing to the side. The water can flow through the soil and exit. We will have a pressure down or spring. The water can flow based on this head difference. If there is no head difference, then there will not be any. There will not be any. But if there is a head difference, then water will. Now, how this water will flow? Basically, you apply the continuity equation, mass conservation equation, and you come up with the equation of continuity. Basically, you apply the equation of mass conservation to an element of water to which an element to which water is involved. And you end up with this is called the Poisson's equation. You end up with into steady bit. Okay. So when there is one also isotopic soil, you will have one square, then square, then square, then square, square. We have basically we have quantity technology. We have two categories of solutions to be fixed. One is the potential function, other is the speed. So the geometry that you have, you basically make a fluid which has some fluids, like this is a fluid, this is a fluid, and then we have flow lines and potential lines will obviously and be with each other. Then we have that given a process of it. Um, then you have that that will make it basically approximately 1 to 1 direction by side. Um, we will make this flow diagram and then we calculate the volume and about the task. And one thing to note is that this flow diagram, flow net, this will be unique to your geometry. If you change the properties of the soil, this will not change. But if you change the geometry, this will change. So streamlines and potential lines. The streamline is along with the lines along which the water will flow. Potential lines are the lines along which the hydraulic head is constant. Okay, let us now move on to the skills and questions. And 5 minute break. Is it okay that we take a 5 minute break? And in review. Result of a constant heterogeneity test on a fine sand sample having a diameter of 1 height and your sample, then we connect it to the output and above it water source. To the water flowing from there and that drainage from there that is draining at a constant discharge. The constant discharge means that this level and this level will keep the building such that on we can say that the time that is taken for this water to do this. We have adjusted the head such that we have achieved the constant discharge from this out. So the constant head difference is 500 mm. Time collection of water is 5 minutes. Once- Okay, volume of water collected is so you know that from Darcy's law, E is equal to K I. So K will be equal to V into how we can say Q equals K I A. And now if you want to calculate the permeability, K will be equal to Q over I times A. And I we know delta H by L length of sample. This will be the discharge over delta H area of the so the discharge is basically 250 centimeter cube per 5 minutes. So Q will be K equals 350 over 5. We have discharge per specific discharge. Multiplied by the N will be length of the sample, one meter split, 300 centimeter area. So it's centimeter distance. Then A will be 5. So H is given is 500 under. With this, if have 5 minutes left, let us convert this into C. If a value of 8 determine the hydraulic conductivity at 20 degrees Celsius. Because in that, um, basically, why hydraulic conductivity will be different at different temperatures. It is written hydraulic conductivity. It's not very important. Because permeability is not as matter how much with and what the temperature is. Hydraulic conductivity we saw was permeability over the and you know that you will have different density and different viscosity at different temperatures. So at a higher temperature, so you will have a lower viscosity and you flow easily. So we have values of temperature of water is at 24. Okay, so these are at 24 degree. We have this I said hydraulic conductivity equals the formula. So hydraulic conductivity at 24 degree will be kappa times rho at 24 times Q over mu at 24, and the hydraulic conductivity at 20 will be kappa times rho at 24 at rho at 20 into G divided by mu of 20. And if we divide both of these, G and G will go, this and this will go, this will move, and we have to calculate at 20 minutes. So, hydraulic conductivity at 24, so hydraulic conductivity at 20 equals this kinematic viscosity mu by rho equal to kinematic viscosity. This will be kinematic viscosity at 54 and our hydraulic conductivity at 20 degrees. Hydraulic. These are constants that we can look for and just to kind of show you that our hydraulic conductivity. I will get this question. But so hydraulic conductivity at 20 degree will be 3 into 2 meter 24 by meter 20 is 0.9 there constant head permeability. Constant head permeability test we do for coastal soils. Why we do that? Is because they are freely breathable. So if you put in water from this opening in the sample, you will not get time to calculate the falling head with the stopwatch because it will drain out too quickly. The water in this standpipe will decrease too quickly for you to measure it. So what we do is instead we try to maintain the head of water and instead we check the discharge. But in falling head permeability test, which is done for fine grained soils, for fine grained soils, the permeability is so less that you can't expect that there will be a constant flow or you will get time to wait and there will be constant flow of water, then you will travel. So that's not feasible for fine grained soils. For fine grained soils, what we do is we connect this permeability mold to a standpipe. We put in water in this standpipe and then we calculate the time, we measure the time it takes for the standpipe to fall through, uh, let us say, usually we take the time at 90, 60, and 40 centimeter heights, and we take the time it took from water to fall from 90 centimeter to 60 centimeter. Then we take it from 60 centimeter to 40 centimeter. And then we calculate the probability based on the idea of this test. For falling at probability test, following are given. Length of specimen is 15 inch. Okay. Area of specimen is 3 inch square. And permeability is 0.0688 inch per minute. What should be the area of the standpipe? For the head to drop from 25 inch to 12 inch in 8 minutes. Okay. So we know we can either simply use the equation for probability that we get the falling what's falling head probability test. In falling head probability test, what we are trying to do is we are trying to see that if it would time T1 or T5. Then we equate the change in the drop at here, here, same. And from here, like in a small amount of time, then we integrate it to the complete time and we get this equation, which you already know. E equals the then more AK If you want, I can derive the situation, but right now, I am assuming that you want it. Okay, so we know our day is 8 minutes. We need to find our A. Length of the sample is 15 inch. The area is 3 inch. The permeability 0.0688. And then we have probability H1 is 25 inch. This 12. So calculate this. 8 into 3 into 0.06. Layer is underlain by an impervious layer. Okay. So permeable soil layer is underlain by an impervious layer. Permeability has been given for the permeability. Calculate the rate of seepage for it in into per hour per meter. If if H equals 3 meter and alpha equals 3 meters. Okay. Thank you. First we need to see what exactly is the height of this thing. This is the slant height. Basically, I have to check this. And direction of seedways, but this is the height of the uh, layer. This is the thickness of the layer. And we can say this is equivalent to, we say, this is H, this will be alpha, the delta H equals, if I take this as S, okay, so this one. So tan alpha S square is to this definition. And we will that S and equals the length of row bed, we can say is Then we will do S rho cos alpha. We got this. We got the length of the. So what will be the hydraulic gradient? Hydraulic gradient is change in head over L, which will be equal to S tan alpha over S of 1. Seepage is just the discharge to full scale and into air. Area for flow is this one. The flow is taking place in this direction. It's not taking place in this direction. It's not taking place in this direction. It's taking place in this direction. So this is how I take, let's say, 1 meter in the direction perpendicular to this convention. We will be excuse me, H of and Q will be KIA equals K is at this sign of A degrees and A is H is 3 meter cos of A. and the flow rate is 2% per meter, right angles to cross section. So the permeable soil layer formed in figure. H has been given as 8 meters, H1 has been given as 3 meters, this has been given as 4 meters, height loss has been given as 4 meters, distance for flow, and we have to divided by cos alpha, this is all that is 8, alpha is 8, A is so what is flow rate. So here is equal to K I A. K has been given, I is delta H by L. Delta H has been given as 3. L, let us say L is S by cos alpha, which is from that out. They use 50 by cos 8. Then we have H1. We need H1 for the area. So what it is, I think it was H cos alpha. So H1 cos alpha, A will be H1 cos alpha, L is S1 cos alpha, and delta H has been given. So Q will be K is equal to to I, which is delta H, is I L, which is so K, area, which is X1, which is 3 into cos C. few more people and try to activity. And we have started to start this. So K1 has been given, H2 is 1.5. K4 has been given, and H3 K3 has been given. So we need the equivalent hydraulic conductivity, which is equivalent to KH equivalent KB equivalent. So KH equivalent will be K1 H1 plus K2 KH3 over as in our H dash and KB equivalent is H divided by H1 by K1 plus H2 by K2 plus H3 by K2, which can be written as the movement side, that is division of H I over K. And the example is KH equivalent will be 1 K 4 H 10 to the power minus 4 into 1 plus equal to into 10 to the power minus 2 into 5 plus 4 into the power minus 5 to 2 over 1 plus 1 and plus 2. Let's calculate this. One seven and 0 7 10 to the power minus 4 and 20. And for KB, we will have 1 plus 1.5 plus 2 over 10 to the power no, 1 over 10 to the power minus 2 plus 1 over 0.5 over 8.4 into 10 to the power minus 2 plus 2 over 2 to 1 to 10 to the power minus 2. This do we will put the services 5 to 10 to the minus 4 to 10 to the second. And our K is going to be K1, KB. That's it for today. This question you can try. This question you can try. Okay, move on. Thank you. Is there any question? Anyone who have a question? Yeah, Ryan, if you have the answer to the question, you can let me know by unmuting yourself because usually when I am in the presentation mode, I'm not able to look at the chat section. Okay, it would have been yeah, it would have been nice. You can unmute yourself and anyone can actually answer when we are the questions. And I would really appreciate. Thank you very much for your help. Okay, I think that's it for today. Let's meet next week. Take care.
Thank you, ma'am.